So, hello everyone. You were not here last week either. Okay, here you go. Okay, hello again, everyone. Yeah, let's continue with this lecture on CMOS MEMS, where we have been studying the process sequence of a CMOS process in a very simple example, an old example of 20 years ago, but it's still representative of many of the steps that you find in CMOS technology anyway. And so I thought I would just go through that because nobody designs microsystems based on Intel's or TSMC's latest CMOS technology with 5 nanometer resolution so far. So we have been studying last time this process sequence that started with some low-cost process, I recall, with the definition of the two wells, the N well and the P well, that will later receive the PMOS device on the left and the NMOS device on the right. And we have proceeded now up to the creation of a gate oxide, on which we have deposited a gate material, polysilicon, about 300 nanometers thick with a sheet resistance of 25 micrometers, which I have explained last time. So now we are continuing with this process. And the first thing is to structure the polysilicon gates. The gate is only needed in the middle, whereas to the left and the right of the gate, there will be a source and a drain to let some current be conducted under the gate in the channel region. And the structuring requires another photolithography mask, which is indicated here by the structured photoresist in yellow. Photoresist isn't usually yellow, it's more reddish, and polysilicon isn't red either in reality. It is some kind of grayish layer, but here it's indicated in these colors. And that photolithography is then followed by some anisotropic plasma etching, vertical etching, so that the structure of the photoresist is really reproduced in this material, in this polysilicon. So now we have this polysilicon, and let's say in this technology of those times, this may be half a micron of width. So let's say tentative value 0.5 micrometers, which kind of coincides with the thickness of 0.3 in the vertical direction. If we think this to be to scale. So now what we have is kind of the infrastructure needed to produce these transistors. And the first step, which requires, again, partial masking of one side and ready access to the other side, as we have seen several times already so far, is then to implant what is called a lightly doped drain, lightly doped source at the same time. But it's called LDD, lightly doped drain, because it's one process. And that means that we are adding to the dopings we already have, namely the doping of the P substrate, and then this P well dopant may be doped to now a concentration of, what would I say, 10 to the 16 per cubic centimeter. And then this threshold implant, the P implant that was added, now we're adding an N implant, because the sources and drains need to be N-doped so that they can conduct electrons. And these electrons can then flow across this P region underneath the gate in an inversion layer that allows these electrons to flow along the gate oxide from source to drain. And this is done actually by a pretty heavy doping. The sources and drains ultimately will be pretty heavily doped. But if you have these very heavy dopings, and by heavy, I mean to saturation, 10 to the 19th, then you also have very strong PN junctions, because you have an NP transition. Yeah? And PN junction with high doping mean high fields. And that means hot electrons. Electrons get accelerated very strongly, and that is not favored because hot electrons can then impinge into the oxide and get stuck there, and then they have their charge stuck in the oxide, and then threshold voltages shift around, and nothing remains stable. So one wants to keep that off, and for this reason, one implants a lightly doped drain. And you see the dopant concentrations now 5 to 10 to the 13 per square centimeter at 50 kilo electron. Well, that's a voltage that is much lower than the one we have seen before, I presume. Let's check that. We have had some 100 kilo electron volts implant, 75 kilo electron implants, and that depends also on the dopant. Yeah, so here it was boron, and now we're implanting phosphorus. Yeah, so there are these technological tables that tell you, at which acceleration voltage, how deep your implant gets. So if you want to hear the details of that, you can listen, you can attend a lecture called Advanced CMOS Technology by Dr. Rute of my group, who teaches that in the detail that I don't teach here. So now this weak, not so strong implant dose, which is higher than the previous one. It was 10 to the 12. Now it's already a few times 10 to the 13. Gets stuck here quite near the surface. And then during the subsequent thermal history, those dopants get built into the crystal, and they get redistributed a little bit, but not very far, because the temperatures don't reach these high temperatures anymore as we had before. In order to redistribute the dopants that created the well, that were implanted at 10 to the 12, no, what was it? Here, much more, 10 to the 13 at really high voltages. We needed then anneals at 1,100 degrees. And during that period of several hours at this temperature, the dopants can diffuse deep into the crystal. And we don't want any such deep diffusions anymore. We want them to stay close. So the temperatures need to remain lower and lower. Otherwise, we ruin what we would like to do. It wouldn't be a good idea to do the drain diffusion at the end, because then everything gets implanted very deeply, and all your trouble is for nothing. So lightly doped drains, and you see that during that diffusion process, well, or even during the implantation, there is a little bit of lateral implantation, the lateral straggle, this is called in the terminology of the CMOS technologists, where a little bit goes underneath the gate, and then we have here an effective gate length that is not exactly the gate length of the gate as we structured it. It's slightly smaller. So the critical dimension, may be the smallest structure that we produce physically, but then electrically there may be even smaller structures, and that is a way to make these distances even smaller, and therefore the transistor even faster, because electrons have to travel less far, and to increase therefore the frequency of the CMOS process. So this is what is done here, and the same is repeated on the other side by, again, photolithography, protection of the right side, and then implantation of this lightly doped drain on the left side with boron. It has to be P into this N substrate, N bulk region, or body region, as it is called, underneath the transistor. And again, similar concentration, similar voltages. So that being done, now there follows a conformal deposition of silicon oxide. And you know that silicon oxide is usually written like this. If you take glass, window glass, or quartz, the ratio of silicon to oxygen is 0.2. But this is a deposition process that occurs in, by some silicon-rich compound, silane or dichlorosilane or so, and then some oxygen-rich compound, maybe just O2, and they combine to form this layer that grows on the surface slowly. And that is not a stoichiometric process. It's as molecules arrive, and if your pressure was slightly off, then you get a little bit oxygen poor or oxygen enriched layers. Of course, process control is an important business, but that's why people are cautious and they say, oh, silicon OX, to say it's about, and X is about 2. Usually there is also hydrogen built into these layers. So maybe not with LPCVD, but low temperature, at low temperature maybe already. So the reason for low T, we know now, if we did high temperature LPCVD, we would ruin the diffusion profiles. So it must be low, and that means maybe 400 degrees or so. We don't go higher now, much higher. The silicon oxide is a 0.5 micron thick, about, and it is called conformal. Now, conformal means covering uniformly all structures. Side walls the same way as vertical structures. If you have an anisotropic process, let's say where you do a physical evaporation from a source, molecules or atoms arrive, and they arrive in a directional way, and then they get deposited as where they can be deposited. And if you have some step, there's no reason for those atoms to go around the corner and cover the sides of those steps. That would not be conformal. But in these processes with enough gas and enough diffusive component, you can achieve a so-called conformal deposition. And we will see that this is an important step because it allows us to do a it allows us to do a structuring which is not, that does not require a photomask. It is so-called self-aligned. And we'll see that on the next slide. So here, whereas the deposition was conformal, the etching of the oxide is directional. We only remove from the top. So you can imagine what the etching gas sees. I'm trying to draw this now. Okay, here is a gate, and of course I should draw a little gate oxide maybe here. Anyway, so here's a gate, and then there is this protection layer, this conformal layer that looks something like this. And now, if we did an isotropic etching from all the sides, we would remove, so I'm drawing this on one side, we would remove, well, a layer, and another layer, and more layers, and at the end, just as this was conformally deposited, would be conformally removed, and nothing would be left. So now the removal is vertical. Whatever etchant comes only gnaws at, or etches, removes what it sees. It doesn't go around the corner. So on this side, it just etches down. So, and here, well, it etches also down, and then a little bit around these corners. So, more and more, and what is left at the end is kind of an image of the structure that you had before. So this is still there because the thickness to etch vertically is twice as thick, or different from the thickness here. Here we only have this thickness, here we have this large thickness. So when we remove vertically a given thickness, we are left with some structure. And this is called a sidewall spacer. That was structured without a photolithography, just by intrinsic technological know-how. Very handy. So now we have effectively widened the gate by these blue sidewall spacers, and that's needed for the subsequent source and drain implants. So first we do the P implant, the phosphorus, or now it says P implant, and then here it says arsenic. Yeah, so this is a contradiction. It's an arsenic implant. Yeah? P doesn't mean positive; it means negative dopant, a donor, and this arsenic is implanted at an incredibly high concentration or deposition dose. 10 to the 15. That's 2 orders of magnitude more than we had so far. So this is a heavy implantation, and at not so high an energy. So it means that lots and lots and lots of dopants get stuck here close to the surface, and then of course during the subsequent history that has some temperatures, then these dopants are implanted, are redistributed at a intermediate temperature for a short period of time. And that means that this big concentration redistributes over a few hundred nanometer of thickness, maybe a micron, maybe half a micron. And when you calculate how much 3 times 10 to the 15 per square centimeter, when they distribute over half a micron, how dense they are, I presume, and you can calculate that to be sure, that the concentration will be high, something in the region of 10 to the 19th or 10 to the 20th. So here we have this strong dopant concentration, and then we still see a little bit of this tail of the lightly doped drain. So from the point of view of the electrons injected into the channel region, they don't have these super high fields right at the beginning where the action is of the conduction. Yeah.
That was going to be my question. Why do we have 2 implantations? That's open so that there's a bit of a gradient.
Yes. The p-n junction doesn't form. The p-n junction doesn't form now here at the end of the high dopant region, but we have this radial transition into the lightly doped region, and then the p junction extends over a larger extent over the lightly doped drain into the lightly doped drain, and the peak electric field is lower thereby. Yeah, so this being done on this side, it's repeated on the P channel side with a boron implant. Again, lots of those at not so much of energy to remain close to the surface, and then there is a drive-in. Yeah, so the drive-in, drive-through. This is the drive-in movie theater in America. No, here it means just we drive in the dopants into the silicon crystal, and this is, as I said, at this still fairly high temperature, but for a short time. And this is to recrystallize the heavy damage we have done by the implantation. First of all, I mean, those atoms come and then they display silicon atoms, and the monocrystalline silicon is no longer monocrystalline, so it needs to regrow from the inside, where deep enough it is monocrystalline for sure. And at the same time, the dopants jump from position to position and take their substitutional positions in the crystal. Yeah. So now we have this the situation with the gate oxide still there. We have these source and drain diffusions of the right doping polarities on both sides, and basically the transistor is kind of ready, but the source and drain need now electrical contacts to bring in charge carriers that can flow underneath the gate or be blocked by the gate. Yeah, so this is the next thing. The oxide needs to be etched. Which oxide? The the thin gate oxide where it is not needed. So here we have this gate oxide and and now it is gone. Yeah, we still have the gate oxide underneath the gate as an insulator from between the gate and the body silicon to have this MOS structure, metal oxide semiconductor structure, where the field effect can then act in the silicon, in the semiconductor part. And so this is done. Etching silicon oxide is no problem. You take some hydrofluoric acid of appropriate dilution, and if you know how long to do that, you can do that, and then you can even in water you can check whether the oxide is gone, because oxide is hygroscopic whereas silicon is hydrophobic. And if your water your water droplets stick to these areas, you know you still have some oxide, and you probably need to etch some more until the water retreats from these areas. So this is a standard trick of technologies to see whether an oxide etching is complete or needs to be continued. And then comes a metallization made of titanium, 100 nanometer by sputtering. So this sputtering is different from electron deposition. There are two physical deposition methods. One is called sputtering and the other one is electron deposition. Electron deposition, what do I say? So in electron deposition, a target is usually heated by an electron beam to a high temperature or resistively, and then metal atoms just escape from some hole and then project linearly onto the substrate where they get stuck. So that's a directional process. In sputtering, everything is done in argon gas, and there is a directional component, but there is also an anisotropic non-directional component, and that's what you see here. Here, the sidewall spacers have been slightly covered, and the field oxide has also been covered sideways, and then of course there is a lot of material on the top of surfaces. So this is the first part. That's again a blanket deposition, a sheet deposition over the entire wafer, and we will have to structure those that metallization. So before this is done, actually there is a thermal process at 650 degrees, very shortly in nitrogen, to form two things. At this temperature, so how is this done? Usually this is such a short process. You can take a wafer in a furnace and then heat it up in a few seconds to 650 degrees and then cool it down again. It takes much longer. So this is done by heavy irradiation with some heavy hot lamps. It's called a flash anneal, for instance, or rapid thermal anneal. And this rapid thermal anneal does two things. Of course, it heats up the surface mostly, because heat comes in, energy is absorbed, and then energy needs time to diffuse also by conduction. And if this is heavy enough and short enough, the heat remains, or the heat energy, the thermal energy remains at the surface, elevating the surface temperature. And then what can happen is that, first of all, the black thing, the titanium, reacts with the silicon into titanium silicide. So that's a compound of titanium and silicon. They do react. If you look at the alloy diagram of titanium and silicon, there are these phases, and the titanium silicide is conductive. It's metallic in nature, and so it forms a clear interface between the silicon and a metallic conductor. And that's not worse than having the titanium directly on top of the silicon, which would also be a semiconductor with a metal. The silicide is actually, it really forms an intimate connection with the silicon. If it's only deposited, you might need some thermal anneals, and the silicon titanium silicide is, let's say, well accepted here in these regions of the source and drain, but it's more than welcome on top of the polysilicon, because polysilicon is a semiconductor. It's highly doped. It has 25 ohm per square. It's a semiconductor that can conduct as well as any semiconductor can conduct. But if you put a metal on top, the metal will conduct better. So in this process, you now form a sandwich of this polysilicon, which is okay, which is welcome to form then, with appropriate voltage, the inversion layer below the oxide. But then you have also this metallization on top, which allows charges to be directed to the gate faster than if you didn't have it. If you would like to switch on your transistor, you apply a voltage to the gate, and that voltage propagates from the location where you apply it along the conductor by charges flowing along. And once the charges, have propagated enough, and the voltage is constant everywhere, then you have the voltage at the gate location where you want to switch on a transistor. And if that takes time, your CPU is calculating slowly. If you want it to work at 3 gigahertz, you'd better have those charges fast, where they need to be. The voltage needs to go there, and that has to do with, of course, the typical time constants. Typical time constant tau for, an electrical signal with a resistor to assume a stable condition once some conditions have changed, is RC. This is the time constant. Whenever you have a resistor in connection with capacitors, if your R is high, your time constant is going to be high. Now, where are the capacitors? There is capacitor all over the place. So the gate oxide, now the gate material, of course, creeps over some field oxide at some point and is contacted, and there is a metal line. And so you have lots of capacitances with respect to the surrounding. There's metal, conductor, insulator, and then some other conductors. So those C's are inherent in the structure. You can't remove those. And so reducing the R as much as possible is important. And therefore we make the polysilicon as conductive as possible. And then at the same time, in this nitrogen, one forms also titanium nitride on top of the titanium. So in some locations, the titanium is totally consumed. Interestingly here, in some titanium silicide has formed. And so the nitrogen can't do anything. The titanium silicide wins. And here we have also both, and here it is also completely consumed. And that titanium nitride is also a conductor. So in this particular technology, the contact to the source and drain is now directed over the field oxide, kind of into the safe region. You have these delicate structures. If you can avoid to have some later harsh processes like drilling holes into some insulator, those technologies have avoided that by moving that aside. In some processes, actually, this contact is contacted directly by some plug and then insulated, and then another metal layer is deposited on top. So that could be a tungsten plug, and then some, I don't know, aluminum or copper metallization. This is also done. But in this particular case, in this showcase, the technology is a bit different. It also shows you that technology is not, given by God. You need to do it this way. It is the invention of the human, and people solve problems and And so obviously those technologies seemed safe, having solved their problem like this. Okay, so this titanium nitride is being structured, can be removed selectively. The silicide remains. So, the formulation of that etchant is certainly also a challenge. And here we have invested mask number 11. What comes next? Next comes an insulating layer. That's again a low temperature LPCVD silicon oxide, 1 micron thick, so thicker, to first of all, again, conformally mask everything, and then to be removed to make this whole thing flat. Because you can imagine that, topography is not desired. At least if you have many layers of metal, and at every layer, you again have more topography building up. You may have very steep walls at some point, and you would like to conducting layers to lead over that topography. The road, the long and winding road, needs to go over it, as already the Beatles sung. And the long and winding road tends to break or to be unreliable if the slope is too high. And that has again to do with this sidewall spacer idea. We have created this sidewall spacer by having some anisotropic etching and some topography. And now if you imagine that you have this topography and you deposit a metal layer as a conducting layer that you would like to structure, if that etching is two directional, you may have some leftovers of metal along those steep walls. Now, if you have metal layers, metal lines running over that surface in this in-plane direction, and then there are these sidewall spacers of metal running into the plane, all those metal lines are short-circuited. Not a good idea. I've seen it happen at a company 25 years ago. I can't tell the name. Microelectronique Marin, our partner in developing microsensors based on their CMOS process, was a 1 micron CMOS process. Then, at some point they had this problem, and big trouble. So the etching condition was not well controlled. You need probably to do some over etching, sufficient over etching to remove even that little piece, and during that over etching, your metal lines also shrink, and so you better have a mask that is a bit larger. But that means that metal lines can't be too near each other, because then it wouldn't be separated, and so on. So it's interesting, and therefore, in more modern technologies, one does a planarization. And this planarization is called a chemical, or is achieved by a chemical mechanical polishing step. These are machines that look pretty dirty, dirty. It could be considered a dirty process. You have these machines with some felt pads, some slurry, cerium oxide, microparticles in some suspension, suspended in a liquid, and then comes the wafer, and the wafer is scraped over that slurry, and material is removed. And if the pressure is right, and the speed is right, and the combination of slurry and material is right, only the top parts will be removed. So you can imagine that only this has a higher chance of being removed than the bottom of such a valley. And by doing this enough, at the end you have a flat surface. And on that, it's very nice to then deposit a metal line, because the spacer problem has solved itself. And so now this insulation layer is structured again by mask number 12. So it's an oxide layer. So it's certainly a dry reactive ion etching process at this level. It's not done by And now we have opened, well, the oxide over the gate. Now, usually that is not done over the transistor, okay? That is done somewhat on the side. Yeah, the transistor is here, and the transistor area, the active area of the transistor is well delimited, a rectangle, and the gate protrudes over the silicon oxide, the field oxide in that active area, and it protrudes over the field oxide, and that's where actually the contact is done. Yeah? You don't want to ruin your precious transistor. Yeah? You leave that alone. So this is kind of unrealistic. So what is achieved here with the drain and source contacts is also applied, of course, to the gate contact behind. And what you now see is that the oxide is open, and now we can do first deposition of a titanium nitride barrier layer, and then a blanket deposition of tungsten is done. So there is titanium nitride, very thin. Can we see that here? Well, some yellowish structure is visible at some location. Not everywhere. It's kind of a subcritical drawing. And that is an adhesion layer, actually. It's a barrier layer, but it's also an adhesion layer. And then tungsten sticks well to the titanium nitride, and it is deposited not totally conformally, but it fills those holes. And these structures here, those are called vias. The vias are the holes across dielectric layers. So you will hear me say via from time to time. And the metal structure in the via is called a plug. So a tungsten plug in this case. Tungsten plug. And those are deposited by CVD. So the tungsten is not evaporated or sputtered. It is done from a tungsten-rich chemical compound which reacts, decomposes on the surface, and the tungsten remains where it is. Okay. So now, again, we have a chemical mechanical polishing. Planarization by CMP. And now we have filled these narrow structures in the oxide by tungsten. This is called the Damascene process. Now, I don't know if you know about history, but the Damascenes were some fighters with some beautiful swords, with beautiful ornaments. And those ornaments were produced by a process that is similar. So grooves filled with another material, colorful artistry. And so you could imagine a groove that where you scrape something over to fill the groove, and then you bake it, and then it is there. So this structure by filling a hole with something is the idea of Damascene here. So technologists are highly cultivated people that go back in history to explain what they do. Amazing to see these words appear. And then there's a dual Damascene process where actually this is done twice. The Damascene is only single Damascene. Okay, I don't know. I'm improvising here, so don't take my word for it. Okay. Yeah. So once this is done, another blanket deposition is done of a metallization that is really neatly conducting. Aluminum or copper. Copper needs another Damascene process. You cannot deposit copper and then structure it. You need to add the next level of insulation, open the structure wherever the copper line runs. You need to deposit the copper and then to planarize the copper. And before that, you need some, again, barrier layer, because copper likes to diffuse everywhere. So that is not liked by the CMOS designers, because their transistors don't work. But in aluminum, it's easier. You can just deposit aluminum and then you can structure aluminum by reactive ion etching. And this is done here by plasma etching. And once this first layer of aluminum, which now runs over the wafer and interconnects transistors to make a kind of a first level interconnection topology of transistors to make some circuitry. Another layer of oxide is deposited. So this is again silicon oxide, OX, and it's called IMD, intermetal dielectric. It's not some fancy dielectric, it's also some oxide-based dielectric, silicon oxide, maybe with some additional, dopants or so to make it more. It's a simple silicon oxide may do, but it's called IMD, intermetal dielectric, or intermetal oxide. You will hear me say that also from time to time. So please remember. And after that intermetal dielectric has been deposited as a blanket, it is structured. Next mask. So which mask is that? Mask number 14. The next level of vias are defined. Those are again filled with tungsten plugs after deposition of some titanium barrier layer, titanium nitride barrier. What was it here? There's many. Titanium nitride barrier layer, they say here. There's different variants. There's titanium tungsten, titanium nitride, and then we're ready to deposit the next metallization. And that could now be continued for a number of times. 4, 5, 6 metallization layers, depending on the complexity of your design and how big it is, how many billions of transistors need to be interconnected. In this simple process, they stop at 2 metal layers, but they say, it could be more, 3 to 6 metal layers for this type of process. In modern processes, you may have 10, 12 metal layers, but then the transistors also look different, okay? Thin FET and so on. And thin FET transistors. And so after this second metallization deposition, what is deposited is the so-called passivation, the passivation layer. And that is usually not a silicon oxide, it's a silicon nitride, or silicon oxynitride, or a sandwich of layers. Because silicon nitride is chemically more inert than silicon oxide, it's mechanically harder, it's less pervasive to humidity, so it protects, it passivates the chip against the harsh outer environment. And silicon nitride has the disadvantage of having a higher dielectric constant than silicon oxide. So that's the reason why one doesn't use silicon nitride at all these layers. One uses silicon oxide because the C has a chance to be slightly lower. And therefore the time constant to be slightly higher than with silicon nitride. Many, many interesting constraints that lead to technological choices. And this silicon nitride now covers the entire wafer, but of course, then everything would be encapsulated and you couldn't run the chip because you wouldn't be able to get any signal in or signal out. So at some locations out in the periphery of the chips, the silicon nitride needs to be opened. So this needs to be removed, and maybe I can draw some white here. So this needs to be removed. And then some metallization patterns are open to access, and then you can do some bonding, some flip chip bonding, or some wire bonding, or some flip chip bonding, or add some electrodeposited metal on top to do flip chip bonding or some other alloys. So this is what it takes, and in this process now, 16 photolithography steps have led to that result. And remember that at every photolithography step, you can build in errors. A little dust particle will also lead to a pattern on the chip. And if those dust particle patterns add up after one process after the other, then at the end you have dust specks all over the place and the chip doesn't work. That's why you have to do this clean room technology under dust-free conditions, which is the harder, the smaller the structures are, because the smaller the structure, the smaller the dust is, the more there is. The air is filled with dust. A few little dust particles, hairs, or little things you can see if the light comes in on a bright day, you see this dust. But if you go down and look at smaller and smaller dust that you can't see anymore, there is more and more of it. So you have to clean that air as much as possible, and that is the clean room classes that you probably have heard about in other lectures. So this is now all a cross section, and unfortunately we haven't seen now the three-dimensional structure. So I would like to make that connection a little bit with this these additional slides that I elaborated many years ago that show you some layouts viewed now not in cross section but from top. How could such masks look like in reality? Because all we have seen is now cut through a mask and what it does to the subjacent layers that are being etched. So in this low-cost process, we have elaborated structures like this that are separated by field oxides to either side, and then either thin oxide or something else small in between. And this field is, of course, viewed from top is some rectangular structure. So the mask that is imprinted, so to speak, onto the wafer is a 2D structure that has this shape, could have this shape of a rectangle. So that in the back and in the front, there's also field oxide. There is a square surrounded by field oxide. In the middle, there's nothing. The active region is a square. And then after many steps, we have ended up with defining the polysilicon structure. So the polysilicon structure will be a line running over that active region, ending maybe slightly on the field oxide on this side and on the field oxide on this side to receive a contact, maybe here, to be contacted with metal later at this location, outside of the delicate transistor region. And let me go back to some other colors. And then for the source and drain contacts. Now here I show you this example where this insulation silicon oxide, yellow, the silicon oxide has been opened with some vias, and now the vias have been filled, and on top there is this metallization. Those vias, those holes are in the form of these little rectangular or square holes that are cut, etched vertically into the yellow silicon oxide. So you might wonder why these little square pieces instead of one little long rectangle. Again, technology is something that requires to be reproducible. So if you can etch a square hole, a hole with square cross section, then you can probably also etch 2 or 3 or 4 of them. If you etch a slit, that's something different. A slit is a 1D object, whereas a hole is a kind of a zero-dimensional structure. Wow, roughly speaking. The etch conditions in a slit object are going to be different than those in a structure that is limited in 2 dimensions. There will be different load factors, and you would like to have this etching progress at the same speed everywhere. And if you have one type of structure, small hole, slit, big holes, you can be sure that at the big holes, the etching is going to maybe be faster than in the small hole. And so once you're finished with the big hole etching, you need to continue etching, and thereby you continue etching whatever there is, and you over etch, and that may not be good. So to guarantee homogeneity, you limit your designs to as few variants as possible, and this is done in this particular way with these via holes. And therefore, a technologist will be able to tell you, yeah, per hole, we have a resistance of so much. And then if you have 10 in parallel, you know that the resistance of the 10 in parallel will be 1/10 of a single hole. And this is how circuit designer can design their circuits if they need to implement this level of detail into their circuit simulation. So the next is this metallization deposition. Now here, it was done basically in a single step, somehow simplified with a mask that covers those vias. Not just critically, going around here and believing that the mask aligner will be perfect, and the technologist just knows how to do it. All these little shifts. So you make the mask over the via a little bit bigger, so that if there is ever such a slight shift, you still cover the via. And I continue here. What is that? Next slide. So for instance, this metallization, it's now to be contacted with a second metal layer. So we need another via etching, shown in brown, and then we need another metallization mask shown in dark blue here to produce these structures, and then we need to open the passivation over the metal. That's the green mask here. So these are all two-dimensional structures, and if you go into Professor Manoli's design lab or into my design lab where we make structures of various kinds, of course, these are always 2D views of layers of things that will happen technologically in a similar way as I discussed before, with different variants and micromachining process and so on. And those 2D structures need to be superposed and need to be mentally translated into a physical reality that is 3D, that has cross sections, as I showed you before. Well, that's the challenge of designing, to have this view of how to realize a 2D cross-section as part of a 3D structure by masks that are essentially 2D from top. It's an interesting exercise. I love that always. And so these masks cannot be freely designed, especially not in CMOS processes. The example of these holes shows you that the technologists want to ensure the stability of what they produce by restricting your freedom, because they know it will be reproducible. And that's a beautiful example of a design rule. Contacts from one layer to the other need to fulfill certain geometrical rules. These are design rules. And when you design for a CMOS process, usually you have a big document. Now it's all online, but I remember having had these thick red, deep red documents, with black printing on top. And you may wonder what the hell with red? Because red cannot be copied on the could not be copied on the photocopiers. It was all black. So this was one level of safety for the CMOS fabs who entrust you with the design rules, to prevent improper dissemination with the methods of that time. Nowadays, and of course, you always sign a non-disclosure agreement when you enter into a business relation with these companies. Non-disclosure, you guarantee that you will not distribute their proprietary information, the rules that make their success to other people, then those whom they choose to disseminate it to. So these design rules may be concerned with minimal dimensions that should not be exceeded, to the minimal direction, or maximal sizes, or distances between structures, or overlaps of masks that must happen or must not happen, positions, and so on. And if you violate those rules, then you're at your own risk. It may be that your structure won't work. In some cases, we ask for a violation, whether we would be allowed to violate something. I mean, when you do a design, then you do a design rule check on the system, and then the system tells you you have 2,576 errors, and then you look for those errors, and then some of them are really critical. Some, you may have forgotten a via between two metal lines, and then you're happy that the design check rule, the design rule checker tells you. In other cases, you may say, is it really necessary? And you pick up the phone and talk to the technology, saying, for my microsystem, I would like to, can I remove the dummy metal? It's disturbing because it conducts thermally, and we would like to make a thermal sensor. And he says, yeah, well, we can do that. It won't disturb the rest, but maybe your metallization in your structure won't be produced safely, at your own risk. And then, of course, as a scientist, you take the risk, and then you see that it works, and then you're happy, and you publish, and found a company, and blah, blah, blah. Well, that's the positive story. Usually you do redesign and optimize and so on, and learn many things on the way. Rules based on systematic tests are backed by statistical process control and technological experience, so they should be respected. And here you see a design rule that tells you that why a via the etching of the IMD, the intermetal dielectric, should only be over metal 1. That's the purpose of this via, to contact metal 1 to the next level, the metal 2 layer. Well, you may say, wouldn't it be great? Okay, if you don't do that, if you do an etching without there being any metal here. So let's assume this blue metal is not here. How does the technologist know when the intermetal dielectric etching is finished? The plasma etcher has some gases that etch some plasma, and that plasma color reflects, or the chemical composition of the plasma reflects the species that are there. If the etching stops on some metal, there may be no longer some kind of species that reflect the fact that the oxide is being etched, because there is no more oxide etching. And so imagine that the plasma color changes, and the guy who looks in the window of the plasma etcher says, now it's over. Let's do 5 seconds of over etch to be sure that it's over everywhere. Maybe I missed a spot, and then he's on the safe side. If that etching doesn't stop, he will continue, and then through the field oxide into the silicon, and then the etching is completed, because then the color will again change. But the distance may have been too far. So these are typical design rules now that you find. So now a few general slides. Who can do CMOS? So you can do CMOS. You need a bit of money to buy some machines. Some university labs have had that money from the state or the national government, like DMES at TU Delft, or the Ann Lurie nanofabrication facility of University of Michigan, Ann Arbor. They have all the equipment that was needed to produce CMOS structures, and they have demonstrated that you see it in their publications. That's of course highly flexible. Usually these university facilities have many other tools also to do variants, but what may suffer is the stability of the processes, because so many different things are done. The machines always run in slightly different conditions, and then an etching that worked one time will not work the next time exactly, and so there is a lot of checking needed. You cannot just run through a process sheet and say, please do that, or they run through and then at the end nothing works. So you need to be need to be there. But you can do lots of variance at the cost of a lot of capital equipment. Then some people do so-called partial outsourcing. So they have some own things that they can do. Maybe they do the oxidations. They don't have an implanter, so they send out the wafers to do some implantation at somebody who has implanters, and then the wafers come back, and then you can continue to do steps that don't cost the 2 million of the implanter that nobody can afford except big companies. That's also, of course, you depend on the quality management of those. You need to maybe implement some test structures to make sure that what you receive satisfies your standards, and the implantation has the right sheet resistance that you expected for the dopant dose that you ordered, and the implant drive-in that you ordered. So that's possible. You can also, if you want to do it the cheaper way, to do it using a foundry service. Foundry. In German, this is called Auftragsfertiger. Foundry. A foundry is also a place where metal is melted, I think. So those are also foundries, but this has nothing to do with metal melting. It's I don't know where the name comes from. I just remember that while I was a postdoc, I read this article by a journalist in the Neue Zürcher Zeitung, very respectable journal. And then they talked about this new silicon foundry, and the guy translated into German, die Siliziumgießerei. And now you have a totally different mental image. Somebody who melts silicon and then pours it into some receptacles and does all kinds of interesting things with it. It's the wafers go into the fab and then they produce chips out of those. And they do it as a service to people who order chips. So TSMC, UMC are foundries. They have no products of their own. They do not produce the super duper, I don't know, digital television or communication chip. They do only these chips because somebody else tells them to realize their design. And so they earn their money by Brötchen backen of the high technology level. They bake the little buns and cookies for other people. But the design of the cookie and the buns is, it's the other people's business, as long as they comply with the design rules of the technology. And then there are smaller companies, AMS, X-FAB. I like X-FAB a lot. We have done many designs in X-FAB. There are also services who are the intermediaries between foundries and customers. So if you imagine that you're a university lab and you would like to buy to have some chips fabricated, but you cannot afford the company to produce entire wafers. So what is done then is done a so-called multi-project wafer. X-FAB has runs where it combines the designs of many university fabs or companies who would like to do an ASIC design on the same wafer. The photolithography is repeated, and each of these repetitions consists of little chips designed by partner A or customer A, customer B, customer C, etc. And at the end of after the fabrication, the wafer is cut into chips, and A becomes chips A, and B gets chips B, and so on. Everyone gets his own chips, 50 pieces maybe, and then he can do the testing and verification and then be happy and say, okay, this worked. Now we'll do the real fabrication because we want to do more than 50, we want to do 10 million. Yeah. So then this is another size of order for X-FAB. Yeah? But until we reach that state, we can do this multi-project wafer run. And there are intermediaries who organize that business. Yeah. So you as A, B, C, and D talk to Europractice, or in America to the Moses Foundry Service. And then they get the designs, they arrange the whole thing, they send it to X-FAB, and X-FAB sends back the chips, and then the chips are distributed by the service provider. Yeah? So we have done both. I know that Janos Manoli, who does microelectronic chips, of course, uses a lot of these multi-project wafers, because it's just a chunk of silicon, and then you need to bond it and evaluate it. In our case, when we do micromachining on top of that, we cannot do micromachining on a little chip. That's not a well-controlled problem. We prefer to have a whole wafer and to do photolithography on the wafer level, and then do our etching there, or deposition of metallizations and so on. That's much easier, and therefore, well, in some cases we team up even with Janos Manoli and other partners here at IMPEC to produce full wafers. So many projects of my chair or of the chair of Janos Manoli team up to fill a wafer, and then we can order X-FAB to produce 3 wafers guaranteed in one of their wafer runs. That's not a multi-project wafer run, because the multi-project is our part. Yeah? We just say, okay, produce the wafer, and we get 3 guaranteed wafers back. And then we cut them into chips and do whatever processing is necessary to make microsystems out of it. So let's look at those materials, because now we have viewed the materials only as part of transistors, but of course, MEMS engineers would like to see more in them. Yeah. So for instance, an N well and a P well to a MEMS engineer is, of course, a structural material. It could be a standalone block, of a thickness. If you remove everything underneath the N well, then you have a thin layer of silicon. You could make a membrane out of it, for instance, for a pressure sensor. But it can also be a thermal conductor. Because silicon conducts well. It's probably not going to be a membrane of a thermal sensor, because whatever thermal things happen will be smeared out very rapidly by thermal diffusion. But it is massive, so mechanical structure can be produced, and also an N well is a very good Hall sensor conductor. The N-type carriers, the electrons have a high mobility, and that is what is needed for a Hall sensor, much better than the positive carriers, the holes, which have about a third as high mobility. Then silicon, the source drain region, well, how could one use those? They're pretty highly conductive, so they could be used as a piezoresistor. Imagine this doping contacted at 2 locations, and then some mechanical constraint. It could be a piezoresistor. It can be part of a thermopile, NP, can be a thermal element, a thermocouple, and if put in series, can be a thermopile for the thermal sensor. Can also use it as an electrode. The field oxide is, of course, a structural material. It's thick, 0.5 micron or 3.8 micron. It is thermally insulating as opposed to silicon. Silicon oxide has a thermal conductance of 1.5 watt per meter Kelvin, whereas silicon has a conductance of 150 or something at room temperature, depending on the doping. So you can insulate well. It is also etchable by hydrofluoric acid, so it can be used as a sacrificial layer, can also be used as a etch stop if you remove silicon in KOH or EDP across the wafer. At some point, you reach the front side of the chip, and then the silicon etching stops because there is no more silicon. And if you don't overdo it, the silicon oxide is a good stop against that etching. It will be etched also, so don't do it too long. And then your membrane is also gone or will break. So it's a method. Then gate polysilicon. Silicon in the form of gate polysilicon is a wonderful resistor. It is a heater, but it's also temperature dependent, so it can be used as a temperature sensor. Can be used as an electrode, a piezoresistor, part of a thermopile again, structural layer. Imagine just a microstructure made of gate by removing the field oxide below. That could be some resonator, but it can also be etched away, just like silicon. Can be a sacrificial material. So here I'm just dreaming. I'm not saying that this is all necessary and important, but this is how creative ideas get started. Not to say, well, could I use it differently? How am I going to use it differently? And what structure would be possible? Is that an option? The other silicon oxides, just the same as the field oxide. Also, they have been used as infrared absorbers. So for infrared sensors, of course, because they're transparent, and they have interfaces with other materials, there is reflection, so there's multiple reflection, let's say, that makes an optical material also to some extent. The metallizations are, of course, conductors. They're also an electrical conductor is usually also a thermal conductor, but those can be electrodes. You should also add others, but those are the ones we have heard about in the CMOS technology so far. Structural materials, sacrificial materials. Passivation silicon nitride is again all kinds of things. Structural, thermal, infrared absorber. So now I have a few slides just showing you some of those companies and what they offer. Now those are not the present state. I did not go to X-FAB to see how their webpage looks like, because it changes all the time. Those companies are active and trying to improve and adding other things and redesigning, and the management says, oh, this is all wrong what the last management did, we need to redesign everything, and then you could just spend your time updating this kind of slides, but the general message is usually the same. You find that okay, X-FAB, for instance, does technology, CMOS technology, and they do also MEMS. They do outsourcing. Interesting. They have services. So this is the message, and then you can go in. And for instance, in technology, see, there are CMOS technologies from 0.18 micron to 1 micrometer. I think now it's 0.13. With X-FAB. There is also bi-CMOS technology. You can also do bipolar transistors at the same time as CMOS. That might be interesting. Bipolar transistors can be useful to make temperature references, PTAT sensors. So if we need an accurate on-chip temperature measurement, that might be a way. A bi-CMOS technology is really more expensive than a CMOS, so that temperature sensor based on a PTAT sensor needs to be questioned. Is it worth it? Or can I do another temperature sensor maybe that satisfies my requirement? They have SOI CMOS. SOI, so there is an oxide layer below silicon. Okay, what is SOI? So usually you have this wafer, and then the active areas and the active structures are built into the surface of the silicon. Now in SOI technology, the wafer is more complicated. You have a silicon oxide, and then there is more silicon on top. So say cross section, there's more silicon, a little thin layer of silicon, maybe half a micron or a micron, depends on the resolution of your technology. And that silicon is where the transistors are being built in here, yeah? So then maybe there is a trench etching that separates one transistor from another transistor, which can have various advantages. So the transistors are in really separate wells, not in the kind of wells that we have seen before that are adjacent to each other. And that solves a lot of problems, like signal transmission across transistors and latch up and electrical problems of all kinds. And so this is a way to do it. They also have MEMS technologies. And so if I look at the CMOS technologies they offer, okay, here is the whole range from high resolution to not so high resolution. There's high performance mixed signal, high temperature, high voltage. Oh, very, very proficient with one polysilicon, 6 metal layers, okay, 1P6M. And you can even do flash memory chips on top of that. So this is really high performance process with interesting options. If you go down here into these less top-notch, some analog mixed signal baseline, 2 polysilicon layers, okay. Maybe if one of those is p-doped and the other one is n-doped, maybe you can do thermal piles and thermal sensors with those. 3 metals, okay, that's fine. 12 volt, okay, yeah, that's okay. If I need a deep well, for instance, to design a Hall sensor, I need a well that is a few micron thick, especially if I do a vertical Hall sensor, as we will see in chapter 3. So deep N wells are usually not available in these general technologies. You need some high voltage process. So I look at high voltage. Okay, so here are some options. It could be that one or the other of these processes offers deep wells. So I will have to check deeply into the information in order to draw this innovative vertical Hall sensor. They have foundry service, they do manufacturing, quality, design support, and so on. They, of course, they have also discrete processes. You can go there and say, based on your basic technology, can I maybe add another metallization? I need this platinum, for my neural sensors. Can you do that? And the technologists may look at it and say, well, we have platinum, so how would you like to have it? How thick? Would you like to have it structured, or shall we just deliver the blanket deposition and do the rest of the photolithography, and so on? So these are options that you can take advantage of. Again, this is a play field for creativity. Also, they have open platform processes for sensors. So you see here relative pressure sensors, infrared sensors, inertial sensors, absolute pressure sensors. So that means that they have already MEMS modules that are under excellent technological control, where you as a designer can now design the geometry to tune the absolute pressure sensor into a certain range. To say, I want to measure between 0 and 10 bar. And the guy next door may say, I would like to measure between 0 and 0.1 bar. So one sensor is going to be bigger than the other. So different designs may be realized on that established process, again, within design rules. And that's, so if we look at here, okay, here we have an outcome of visibly a pressure sensor. I have no doubt that this is a pressure sensor, where we see this micro machining from the back of the chip leaving a silicon membrane, which is underneath here. And then there are contacts which contact probably diffusions that, well, let's see here. Well, it's not so well resolved, but for sure there will be some diffused resistors in these areas that allow to measure the deformation of that pressure membrane when a pressure difference is exerted onto the pressure. And the size of that membrane determines the range and the linearity and everything. So you can have something realized according to your wishes. So for different pressure ranges, as you see here. Okay, then here's another pressure sensor design with a closed cavity. That's interesting. So the company for sure goes through a process where they provide wafers that have already a prefabricated membrane inside. So they produce a silicon wafer by some wafer bonding process and back edge process by preparing a wafer with this kind of cavity and then bonding a second wafer on top, back etching that wafer to the final thickness of the silicon membrane thickness, and then doing a CMOS process on top of that front surface that looks as silicon to the CMOS technology, but it has these buried cavities underneath. And when a pressure difference is now exerted, or pressure is exerted here, let's say there's some residual pressure P0, this delta P equals P minus P0 causes a deformation of that membrane, and therefore some deformation of those piezoresistors, these P implants, which then will allow you to extract an electrical signal somehow related, hopefully linearly proportional to that difference P. And if P0 is virtually zero, vacuum, then this is an absolute pressure sensor. That's what is meant by absolute pressure. Okay, here's some infrared sensors. What do we see here? So I bet this is silicon down here. This is micro machined silicon, a cavity across the wafer. Here we have the field oxide in green, and then we have some interesting conductors here that are connected on the silicon on the silicon oxide membrane, and then passivated somehow. And we have here other contacts. So that's a typical thermocouple. If the temperature at this location is T0, and here we have T0 plus delta T, because I don't know, some radiation impinges, infrared radiation impinges on that structure, then there will be a voltage delta V that can be measured between those two contacts. And that voltage is proportional to, so delta V is proportional to delta T. And the proportionality constant is called the Seebeck coefficient or thermal power, and we'll see all of that in the chapter on thermal sensors later. Just as we will also look in detail at this kind of sensors when we talk about piezoresistance. Here are some inertial sensors. So this is based again on some more complicated silicon substrate made of several layers. It looks like a silicon on insulator substrate that can contain some circuitry outside of this region here. And this region is then packaged by an additional top cap, an additional silicon structure enclosing some delicate micromechanical structures, vibrating beams, forming capacitors that are able to measure the acceleration of the structure in the plane, for instance, to do an accelerometer or a gyro, as we will see in the last chapter of this lecture later during the semester. Here you see some top view. You see some of those structures, how fine they can be, little beams running over the surface of the structure and being anchored on the wafer sideways, but then able to move with respect to each other to translate some inertial effect, some inertial mass effect into an electrical signal. And one company that I knew well was also Austria Mikrosysteme, which is located close to Graz in Austria. They used to be a pure CMOS foundry, fab and foundry, and they have now developed into a multi-sensor group, like TDK, who expanded and finally engulfed Micronas into Micronas TDK to round off their sensor portfolio also with Hall sensors, in addition to many mechanical and inertial and other magnetic sensors they already had. And so AMS looks like a little bit like the sensor Bauchladen, as we say in German, you have all these different things. What would you like to buy? And so there is light sensors, there is light sources. AMS bought Osram last year, I think. Osram is Goliath. AMS was David. David and Goliath. Goliath won against, and David won against Goliath. They could, convince some investors, to give them enough money to just buy Osram. So now they're really big. So AMS has expanded a lot, and I don't even recognize the company anymore. But if you go into the webpage, you will see that they do also magnetic sensors. They're a big competitor of Melexis, also another magnetic sensor company. I don't know how much they compete with Micronas. Could be, but I haven't heard the kind of big fight that has opposed Melexis against AMS. So they do lots of things. So of course, at the basis, they also do CMOS technology, also down to the 0.18 and maybe now even further down with all kinds of options. Hall sensors, optical elements. Okay, in CMOS technology, good. Good to know. High voltage. High voltage CMOS, that's probably also technology could be used for vertical Hall sensors and so on. I don't know if they do it. And so more details about what those technologies are doing. So what do we see? We have, for instance, this 35, means 0.35 micron CMOS technology. Here you see it. The MOS channel length is 0.35 micron. Operating voltage so much. How many masks? 14. Okay. Number of masking layers. Okay, some masks are reused. 19 different masking layers. Okay, so that's fairly complex. Not very complex, but fairly complex. How many layers? 3 metal layers, 2 poly layers. Is it P and N? Could be interesting. They don't say it. And then some design rules already. How fine can we structure those structures? So the metal 1, 2, 3 can be 0.95 micron in pitch. Pitch means the period of the arrangement. It's not the distance, the spacing, or the width. It's the distance between middle to middle of structures. So every 0.95 micron, you can have a metal 1 layer. Every 1.2 micron, you can have a metal 4 layer. Those are thicker and probably can't be structured so finely and therefore the pitch is larger. Poly 1 pitch, poly 0.8, and then high resistive poly. Do they have that? Not here, but here, 1.2 kilo ohm per. Now that should be a square. They couldn't write square. Yeah, it's number, Gartenzaun. Yeah, but they sure mean kilo ohm per square. No doubt. Yeah, then we have precision capacitors. Oh, the circuit designers love that. So and so many femtofarad per square micrometer, and so on and so on. Yeah, so all this is information that can translate into designs and options and ideas. Well, let's get over this. This is yeah. Then APM is now another kind of service provider. Asia Pacific Microsystems is in Taiwan, in Hsinchu. Hsinchu is a town south of Taipei, about an hour away from Taipei, where all the big foundries are, the TSMC, UMC, and many secondary industries that feed those and pack up to packaging, and then it's a whole technological ecosystem. Yeah? All of Hsinchu is basically technology oriented. Yeah, so you see these motorbikes by the hundreds of thousands, in the morning going to the fabs and others coming out, and it's a big mess, and you know that now it's a shift change, and in the afternoon it's again the same thing, and in the night it's again the same thing. So it's absolutely fabulous, and I mean they live of technology, and they have the best technology. TSMC is really a leader, and so Asia Pacific Microsystem operates in this ecosystem as a service provider for not so top-notch technology, but versatile technology for people who would like to do microsystems using different combinations of processes, machines. And so you can talk with them if you have some original idea that the standard fab cannot produce, or some post-processing that they might do. You don't have to have your own lab if you don't want. Yeah, you can buy things and outsource everything. That's the fabless model. Of course, every outsourcing costs, and at the end, it's the product price that determines whether this model works. Do you trade in investment and the cost that reflects itself on the product, and all the trouble of the investment, or do you outsource the trouble of the investment and then you have to pay a little bit more? So the answer is not clear. Business people deal with this kind of issue to find a niche where they can organize something that is a bit cheaper than the competition, and they enjoy when the product works. So you see there are complicated microstructures, all kinds of etching, suspended structures, bulk microemission, surface microemission, CMOS and MEMS integration. They have really very flexible technology. All kinds of metals that you will not find in the standard CMOS technology. Platinum you don't find in CMOS, but of course they offer you platinum and silver. You wouldn't find silver in a CMOS technology. All kinds of original dielectrics, PSG, phosphorates, phosphor silicate glass, and borophosphosilicate glass, and so very flexible. And then finally, I show you something which I think doesn't exist anymore. Sandia National Laboratory, I've been checking it, but it used to be a foundry service for producing micromechanical structures, purely for that. So it's not a CMOS foundry. It was a foundry for micromechanical structures made of polysilicon, but of polysilicon with many, many layers. So you see here some gears, some interesting mechanical structures that have some dented wheels that move around, that can be pushed into rotation by some structure, some electrostatically driven structure to translate this linear motion into circular motion, or vice versa. And then at some other place, some mirror will erect itself, to reflect some light into a direction, and you can change the angle of that mirror. So there were all kinds of different structures. You see these layers of polysilicon, yeah, here superposed, yeah, to make kind of vertical electrodes, yeah, like electrodes that are etched into a single material vertically, but here in different layers. But by using different layers, they can produce micromechanical structure. So here it says poly 0 to poly 4. So there are 5 poly layers. Yeah, and those top 4 layers can be used as micromechanical layers. Yeah? Just to show you how such a little turning structure might work, let me consider I'll take some yellowish structure. Yeah, so I'll design that like this, yeah, in cross section, and I do the green structure, the poly 2 on top of it, yeah, but I deposit it right through a hole. Yeah. Now, what is white here? So like this. Well, actually, it doesn't need to be so long. Yeah. So, ooh. Okay, sorry, need to go again to that correction mode, like this, and wow, okay, maybe, that was trick 75B, yeah. So now, how does that look like? Maybe I draw that in perspective a little bit, half perspective. So this is kind of a plug, yeah, that stands there in the middle, and then we have this rotational structure that goes around here. Yeah, and the other half is in the front. Yeah? So by depositing 2 such layers, a yellow and a green one, that are obviously separated by dielectrics during the deposition, which are now removed, you have this yellow structure stuck by a green structure. It can't escape. And if you now somehow can start to rotate it by some electrostatic effect, there will be some rotating structure. And if you give it some little teeth, then it can also interact with another structure that has little teeth and get that other structure to rotate at another speed. So this one may turn at 1 million per second revolutions per second, and the other one will turn at 100,000 revolutions per second, whatever you want. So that was a big hype, and this is actually how MEMS technology started, with this kind of ideas in the US. In around 1987, the surface micromachining was demonstrated based on polysilicon micromachining, and people were all enthused, and then conferences were founded and groups were started, and everyone was excited. Yeah, and now the MEMS world looks different, but it's still quite exciting. Oh, I need to stop now. You can also tell me that I need to stop. Yeah? I will talk forever. Yeah? Okay. Sorry. Thank you for your patience, and we will meet again tomorrow at 2:15. Yeah, in the other room at the top of building 51. Okay, the room 03026 for those who were not there last week. Yeah, this has changed. It's not in the ground floor, it's in the roof floor because we have more space there. Okay, see you there. Bye-bye.